All right, I went back a little bit here. So asteroids. We'll start with asteroids. Generally rocky bodies, although we're going to find that some of them are actually more metallic, and there's some carbon rich ones as well that are particularly dark. Most asteroids, as I mentioned before, are found in the asteroid belt. That's not all of them, by the way. There's also some that orbit about 60 degrees in front of Jupiter and 60 degrees behind Jupiter, which are called by the way those points 60 degrees in front of Jupiter and 60 degrees behind Jupiter, that those are called the Lagrange points, or they're part of the Lagrange points. I'll talk a little bit more about those later, but so those asteroids are called the Trojan asteroids. All right, so let's start with Ceres. So originally, Ceres was classified as an asteroid. It was the first one discovered. Just to let you know, it's no longer classified as an asteroid. It's large enough to actually be considered a minor planet or a dwarf planet. Sometimes it's called a dwarf planet. Sometimes it's called a minor planet. It means the same thing. There's this thing called, well, some books call it Bode's law, or Bode's rule. It's not. Yeah, it's nothing. There's nothing scientific about it. Okay, it's not. It's not a real thing. It's an interesting coincidence, as we're going to see. The combined mass of all the asteroids is less than 1/1000th of the Earth's mass. Just to let you know, I mean, there's, you know, all right. Well, anyhow, all right. So this is where this is where the asteroid belt is. This is kind of where I left off last time. There's of course the orbit of Ceres, the largest. Well, it's actually considered a minor planet now, as I mentioned. All right, so we're going to have a lot to say about this, as I mentioned before, here is Jupiter, 60 degrees in front of Jupiter and 60 degrees behind Jupiter are the Trojan asteroids. All right, so they're not, not all the asteroids are found in the main asteroid belt. In fact, there's some asteroids that are orbiting right around the distance between Earth and the Sun. As we're going to see, those are called NEOs, near Earth objects, and they've been studied. There's like more than 10,000 of them, and we've been studying those for a long time because they could collide with the Earth, and that's something people are very concerned about, of course, because one of these things collided with the Earth. It was either an asteroid or a comet that collided with the Earth 65 million years ago and wiped out the dinosaurs. We would like to avoid that from happening to the human species. All right, so this is sometimes called Bode's law. It was noticed a long time ago. It's just this crazy. All right, so anyhow, here's how it goes. All right, so I'll just go through it. It's not at all accurate, especially like when you get out to Uranus and Neptune and certainly Pluto. It doesn't follow this thing called Bode's law. It's a coincidence. All right, so you start with 0, 3, 6. So you double 3. Okay, so that's this first column. And then you add 4 to it, and then you divide by 10. And that happens, just coincidentally, happens to be about what the planets in our solar system are at, right? Notice, right? So using Bode's rule, there should be a planet at about 0.4 astronomical units, and of course that's where Mercury is. There should be one at 0.7. That's where Venus is. There should be at 1. That's where the Earth is. Mars. So see, it starts to deviate just a little bit. Mars should be at 1.6. Notice there's another one that should be about at 2.8, and in fact, that's in fact where Ceres is. That's why they thought for a while, when Ceres was discovered in 1801, it was thought of as a planet. Um, but like I said, later on they found other objects right around this orbit. Ceres was just the largest one. They found Vesta and Pallas and other asteroids, and they reclassify these as asteroids. And then notice that Bode's law works really well, or Bode's rule. It's not a law. Like when something's a law, it describes something with some physical reality. Notice Saturn is a little off, Uranus is off, Neptune is really off, and then Pluto is nowhere near what it should be according to Bode's law, or Bode's relationship, whatever the heck you want to call it. It's nothing. It doesn't even work at all for the exoplanets, right? Planets around other solar systems. So it's just a coincidence. Humans love to see patterns and stuff. So anyhow, what's important about this is using this crazy idea. We started looking between Mars and Jupiter, and in fact, that's and Ceres probably would have been discovered anyway, but it was discovered relatively soon after this law, this supposed law, which is not a law, by the way, said that there should be something there. All right. Anyhow, so let's leave this. Okay, for now, because we'll just leave it because it's not anything important. The only thing important about it is the historical emphasis on having astronomers look between the orbit of Mars and Jupiter, and that's when they discovered the what was then called the asteroid, or actually it was called a planet originally, Ceres. All right, so Ceres is actually large enough to be to self-gravitate into a round shape. One of the next largest asteroids is called Vesta. There's another one called Pallas. So Ceres, Vesta, and Pallas are. And by the way, we've actually visited these with spacecraft, with the Dawn spacecraft. I'll put some videos in there to show, some of the stuff that the Dawn mission discovered. Ugh. All right, so let's see. So asteroids can range in size from 1,000 kilometers across, like Ceres, to less than a kilometer across, like Idawaka. There's Gaspra is another one. These two are actually really interesting, Ida and Dactyl. This is a lot of them are very odd shaped, right? They're some of them kind of look like potatoes. Ceres happens to be large enough to gravitate into nearly a perfect sphere, but a lot of them are very, very strange in their shapes. It looks like there was collisions that occurred. Ida and Dactyl. In fact, we didn't even know about Dactyl until we sent, I think it was the Dawn spacecraft. It was some spacecraft. I don't remember which one. But they noticed that there was an asteroid orbiting another asteroid, right? And so in other words, Ida had its own little moon, and it's called Dactyl. All right, so Matilda. So these are just some other asteroids. There's thousands of them. Okay. So here's some more. And some of these are Eros. This one, I think we actually landed a spacecraft on this one, if I remember correctly. All right. Anyhow, a lot of these pictures are from actual spacecraft that visited these worlds. Some of them even orbited, and some of them even landed on the asteroids. So they're different shapes. They're kind of leftover debris in the solar system. It's leftover stuff that the solar system is made of. There's not enough material there between Mars and Jupiter to actually form a planet, even a planet as small as Mercury. So there's just not enough matter there. Ceres, as I said, was reclassified in as was Pluto in 2006, so it's now called a dwarf planet or a minor planet. There's the density of Ceres is about 2.1 grams per cubic centimeter. There's a lot of ice that's involved there. Vesta is actually really interesting. When we landed the Dawn spacecraft, or orbited Vesta with the Dawn spacecraft, one of the things that we discovered is there's a huge chunk of Vesta that's missing. I think it's in one of the polar regions. And it looked like something crashed into Vesta in the very early stages of the solar system, and part of that material is now in the asteroid belt. I mean, it might be one of these other ones, but in other words, it lost some of its matter, and so it once was even bigger, perhaps even roughly the size of Ceres or close to the size of Ceres. Let's see. This was Itawaka. This was visited by a Japanese spacecraft, and it was discovered to be almost like a pile of rubble. I mean, it almost looks like that, right? And it's just gravitationally attracted to itself. Reflective. So we, when we get reflections from these things, we can pass the light through this material called diffraction grating, which is basically like a prism, breaks up the light into its different colors, and that tells us something about the material that makes up this object, without actually visiting it and scooping up some of it and taking it back home to Earth to be analyzed. At any rate, we can do that. And there's in some instances, like in this one, I think the Japanese did actually scoop up a little bit of it and bring it back. But generally we don't do that because it's just to be too costly with all the asteroids that are out there. So one of the things we do is just look at the light that passes close by, or bounces off these objects, and that can tell us the composition. So generally we find carbonaceous objects, mainly made of carbon. These tend to be the asteroids that are closer to Jupiter. Silicate bodies, that they tend to be closer to Mars, and then metallic iron and nickel objects, which are actually scattered throughout, but kind of fall in the middle. The inner asteroid belt tends to be the silicate rich. The outer asteroid belt tends to be the carbon ones, which are harder to see. They're not shiny. Some asteroids look like loose clumps of rubble that just happens to be stuck together. Let's see. So iron meteorites and those with the spectral signatures of iron have originally been large enough, it's sometimes probably even tens of kilometers, to melt and differentiate. In other words, iron ends up in the middle, and there's radioactive heating. Collisions, break these things apart, and that's what we're left with.